I'm Yuhao Wu. I'm currently a final year PhD student at Washington University in St. Louis. So today, I'm happy to share our research on securing large model-based agentic systems through execution isolation. So my goal with this talk is to convey 3 key points. First, LLM have introduced a new computing paradigm which resulted in emergence of agentic systems. The new paradigm is very powerful, but it also comes up with some new security and privacy risks. Second, existing efforts to secure LLM-based agentic systems are mostly focused on making model more robust. But these methods are effective, but they are currently not foolproof. Third, we believe that traditional system security principles can also enhance the security of agentic systems and, in fact, complement the model robust efforts. So when we say an LLM-based agentic system, we are referring to a system where there is a LLM serve as a logic engine that can access and orchestrate various resources to fulfill a user query. So these resources include memory, storage, and apps, which are also known as tools. So they allow LLMs to take actions in the real world. For example, if you ask the LLM or the agentic system to summarize your emails, the LLM determines that it needs to talk to the email client, fetch the content, summarize it, and then deliver the response to you. So in these systems, LLM need necessary information for each resource to orchestrate them properly, right? So LLM typically have a shared context window that combines user queries, system instructions, conversation history, and tool-related data. However, since their resources and data come from various sources, which may not always be trusted, and their mixture in the shared context window actually pose some security risks. So to say how serious this can get, imagine the user want to summarize the emails from the sales team in their emails inbox. However, one email could have malicious instructions telling the LLM to steal files from the cloud drive and send it to elsewhere. So in a typical agentic system, the email text simply gets appended to the context, and the LLM may treat those instructions as a valid command. The LLM will then call a cloud drive app or cloud drive tool to fetch and forward data to attacker-controlled email or servers. So this kind of exploit, also known as indirect prompt injection, is surprisingly easy when everything is in a shared context window without any isolation. So the key security issue is that instructions from various sources without any safeguards are treated with same privileges in the shared context window. So a version of this problem has actually existed in prior computing systems, and it is tackled with execution isolation and access control. So for example, web browsers use a set isolation and the same origin policy to keep malicious code in one tab or website from infecting another. So in this paper, we explore whether execution isolation and access control can also help improve the security of agentic systems. And there are mainly 2 challenges. So first, you know that agentic system involves so many dynamic and unpredictable collaborations between tools and the LLM. So this is very different from the traditional computing system where interactions are often predefined and very limited. Second, interfaces between components in agentic system are based on natural language. So this is make it much harder to examine the interactions between the LLM and the tools compared to the well-defined programming interfaces in traditional computing systems. So to address this issue, these challenges, we explore a security architecture in this paper. We call it IsolateGPT. So in IsolateGPT, each tool is executed in a isolated environment, which like a separate sandbox with context window dedicated just to that tool's specification, inputs, and outputs. So this is fundamentally different from a typical agentic system architecture, where all tools' input and output are put in a shared context window. So if a malicious string enters the email tool's environment, it won't immediately corrupt the cloud drive tool's context. But you can imagine that this also raises an important question. How do we decide which tool should we route our query to address if all the tools are separated? So that's where a planner LLM comes in. The planner has a synthesized overview of each tool's capabilities and can decide which tool should be used to handle the user query. So for example, if you're asked to summarize your latest email, it routes the request specifically to the email tool's isolated environment. So of course, many real scenarios require multiple tools. So we need additional module or mechanisms to safely collaborate and share data across those isolated tool environments. So we introduce operators, which are responsible for exchanging messages between tools. These operators are non-LLM modules, which can also validate the format and the content of the shared messages between tools. Message checking makes passing some malicious content much harder, but it doesn't eliminate all risks because we still allow string messages to be shared between the tools. So IsolateGPT also relies on user oversight, especially for some sensitive operations. If a user tries to send a message externally or perform any sensitive operations that the planner LLM doesn't originally intend, the system will alert the user and ask for explicit permission before act on that operation. So this step ensures that even a subtle or well-crafted malicious prompt or malicious message can be stopped before it does damage. Putting all those modules together, we have the complete IsolateGPT design. So to figure out how much IsolateGPT can enhance security, we extended an LLM security benchmark and tested IsolateGPT with various attacks, such as compromising tools execution flow and stealing data from tools. We also introduced a non-unprotected system as a baseline. So in the unprotected system, around 20% of these attacks succeeded. But with IsolateGPT, most attacks fail because malicious instructions cannot cross the isolated boundaries. When a cross-boundary request occurs, the user is always alerted. If users follow the alerts to deny all the dangerous operations, the attack success rate can drop to 0. So another key concern is whether these new components might break the normal functionality of agentic systems. To address this, we run IsolateGPT through several benchmarks, covering several tasks, including multiple apps. So we found that IsolateGPT produced final results equivalent to those of the unprotected system in most cases. So even if a system took a slightly different execution flow to accomplish the same goal, the final output was semantically equivalent. So in another word, IsolateGPT doesn't undermine the functionality of agentic systems. Naturally, the new component can also lead to some overhead. we measure how much this impacts the response time on the previously mentioned benchmarks. So we found that for around 3/4 of the tested queries, the slowdown stays under 30%. So while tasks involving more tools can take longer, most real-world tasks currently involve only a few tools. So for such typical scenarios, users may not experience noticeable delays. We also have some optimizations in our paper to further reduce the overhead. So if you are interested, you can check our paper. In conclusion, the new computing paradigm introduced by LLM is tremendously powerful, but security is often an afterthought. We believe that traditional computing system security principles can improve the security of agentic systems while complementing LLM robustness efforts. Our proposed IsolateGPT demonstrates the feasibility of access control and execution isolation in agentic systems. And we also demonstrate that these mechanisms are highly effective at improving the security of agentic systems. So our research provides an infrastructure on which many other security solutions can be complemented and added. So to foster follow-up research, we also open source our code. Yeah, that's conclude my talk. I'm happy to take any questions you may have.
Okay, question from the audience. So while we are waiting, maybe I will start with one question. So after you come up with your system, how do you think about adaptive attacker who can actually evade your defenses? Do you think about any, advanced attacks that can succeed even if after deployed isolation?
Yeah. So you mean, yeah. Basically in isolation, we try to protect the malicious data sharing activities between the tools. But you can imagine that if there is just one tool and there could be some malicious instruction from that malicious tool that can directly steal the user data or create some harm, which cannot be protected with execution isolation.
Okay, thanks. We have room for one last question. Please.
Hi, great talk. My name is Jen from Indiana University. So I'm wondering whether your proposed framework is compatible with some existing LLM agent systems. So for example, given an LLM agent systems, how to incorporate your framework into those existing applications?
Yeah, thanks for asking this. So we originally implement our framework using LangChain, which is a very popular LLM development framework. And to foster follow-up research and maybe public usage, we also work with Llama Index, which is another popular LLM development framework, to integrate our framework to their library so that you can directly use by invoke the library.
One more follow-up question. So I'm just wondering, like, how this framework can be used in the multi-agent systems. I think, is there like any differences, or do you need to add any extensions for make this system compatible with those like multi-agent systems?
Yeah, that's a very good question. So actually, there are a lot of multi-agent systems, but a lot of multi-agent systems do not have like a security consideration. That's why we want to use our IsolateGPT to build such a security guarantee for like multi-tool collaboration, something like that. But definitely, when you try to design a multi-agent system, you can definitely take some inspiration from our system because we have more security considerations.
I see.
Yeah.
Thanks. Great talk.
Okay, let's thank our speaker again.